We are starting with Unit 12 today. Unit 12 is all about solution chemistry and equilibrium. We've used the term aqueous solution before. We know an aqueous solution is when a substance is dissolved in water. Well, a lot of chemical reactions are actually best facilitated by being in a water environment or as an aqueous solution. We know our cells are mostly water. All of the chemical reactions that go on in our cells are going to be in an aqueous environment. So solution chemistry is studying the chemical reactions that are created in solutions of usually water. Our first lesson today is on solutions and solubility, and it's pretty much hopefully a general review for stuff that you've mostly learned before, but I think it'll kind of establish us in a good foundation for jumping off and moving forward with this. So solutions and solubility. Why do chemists never encounter problems? Because they have all of the solutions. Okay, so let's do some definitions. You know, definitions are my favorite thing ever. Just kidding. Okay, a solution is a homogeneous mixture of two or more substances that are uniformly mixed and therefore look the same. So an example of a solution would be salt water. That is a homogeneous mixture between salt and water. Okay, a solution is made up of two parts, a solute and a solvent. Oh my gosh, I bet you can figure out in salt water who's the solute and solvent. Let's see. A solute is the substance that you have the least amount of. So in this case of the salt water, it would be the salt. The solute is the thing that gets dissolved. Now the solvent is the substance that you have the most of in amount. Most commonly, it's going to be water as our solvent. And it's the thing that does the dissolving. Now these two terms, y'all are gonna, all of the S terms in this unit, you're like, what is even going on here? I agree. So the best way to remember that the solute is the thing you have the least of that gets dissolved is I think solute, it makes me think cute, like a cute little solute, okay? I also see for solvent, vent has got a V in there, and that makes me think of like a container that the cute solute is falling into. I don't know, that may be a stretch, but that does help me because these two terms are look very similar to me. But a solute and a solvent come together to make a solution. Okay, I wanted to go over this. This is what the process of solvation actually looks like here. This is the process of making a solution. Okay, so first I'm obviously going to drop the cute little solute into the solvent, so it enters into the solvent, and then the solvent particles are going to surround the solute and eventually draw it into solution, and eventually all those particles will mix evenly. Okay, so I love this picture because you are seeing that these orange and blue things, they are not like chemically combining together. They're just mixing evenly throughout. So this keeps in mind that this is just us making a mixture, meaning no chemistry has been done. This is a physical process, dissolving something. Okay, types of solutions. Y'all, when the solution, or when the solvent, meaning the thing that does the dissolving, is water, that solution is called an aqueous solution. I know probably it's supposed to be called aqueous, but I say aqueous, and I cannot change it after 40 years. I will say aqueous. Okay, and that's going to be the that's going to be the solution that we are going to be dealing with in this unit in chemistry is aqueous solutions. But a solution doesn't always have to have water as my solvent. Or you don't even have to have a solid solute dissolved in a liquid solvent. Solutes and solvents can be all combinations of states of matter, solids, liquids, and gases. You're like, oh my gosh, are you for real? I am for real. Vinegar is a combination of a liquid solution, meaning two liquids are dissolved within each other. Vinegar is made of acetic acid and water, so we have a liquid going into a liquid. Y'all, soda is an example of a gas-liquid solution. Guess what makes your soda fizzy? It's those carbon dioxide bubbles on the inside. That's why we say carbonated beverages are carbonated. That means we have carbon dioxide, yes, dissolved in there. So my carbon dioxide gas is the solute for that type of a solution. And y'all, if we even want to make this stretch, air in the atmosphere is a gas solution. We know there's many different types of gases that make up the atmosphere. They are mixed evenly throughout, so we have a solution of different gases. So lots of different types of solutions, not necessarily something dissolved in water. But for chemistry, that's really what we're focusing on, with water being the solvent when we talk about solution chemistry. Okay, as I mentioned before, making a solution is a physical process. So because it's a physical process, I can actually separate my solute and my solvent away from each other by physical means, like evaporating my water off to reveal the solute left behind, filtering my solute through a filter paper, any of these physical methods of separation that we've talked about before. Okay, more S terms. You're like, oh my gosh, she's crazy here, and I am. In chemistry, to dissolve something means to mix a solute evenly into a solvent to form a solution. In forming a solution, sometimes things don't always work out the way we would expect it to. We can classify solutes as either being soluble or insoluble. Now, soluble means when the solute can be dissolved in a solvent. So here I've got my black little solute particles mixed pretty evenly throughout with the white particles here. Okay, that looks like a uniform solution to me. We would call that black substance a soluble solute. Now, down here, insoluble, that's when the solute cannot be dissolved in the solvent. So my poor little black solute down here, he is not mixing evenly with the solvent to make a uniform solution. So we would classify him as being an insoluble solute. And maybe some of you guys are thinking, oh, soluble, insoluble, like our solubility rules that we learned back when we did chemical reactions. Yes, and we're actually going to revisit those solubility rules again here a little bit later in the unit, now that we know a little bit more about solutions, which is really cool. Okay, so solubility, this term for solubility, you're like, great, it's how much, it's the ability to dissolve or not. Well, it kind of relates to that, but it's a more technical term. It's an amount of something that can dissolve. So solubility is the maximum amount of a solute that can dissolve in a specific amount of solvent at a given temperature to form a saturated solution. We're going to go over a lot of these little what's called solubility curves, but what this is showing is basically what the definition of solubility is. It is showing up here on the y-axis the amount of solute in grams per 100 grams of water. That 100 grams of water represents that given amount of solvent. So here water is the solvent. I want to know how many grams of my solute can dissolve in 100 grams of water at a certain temperature. So if I look at the x-axis, I have temperature increasing this way. And then it looks like I got a weird line thing here, okay? It looks like something is changing or solubility is changing with an increase in temperature. I also have some labels on here: supersaturated, saturated, and unsaturated. We're going to unpack all of these terms here in a second. But yes, the solubility of a solution can be classified as one of those three terms, basically: an unsaturated solution, a saturated solution, or a supersaturated solution. Okay, let's talk about each one of these. A saturated solution is a solution that has the maximum amount of solute that can dissolve. Now, this is dependent on temperature, as my solubility curve is showing me. Now, it says when you add more solute, no more can dissolve, okay? On a solubility curve, that's what that line is really representing or showing us. It's like, hey, how much in grams of that solute can I cram into 100 grams of water at a certain temperature? That's showing where a saturated solution would be represented by. Okay, so saturated, that makes sense. Now, unsaturated. An unsaturated solution has less solute than the saturation amount. So when I add more solute, it keeps continuing to dissolve, and it will continue to dissolve until it reaches that point of saturation. Now, I thought I would kind of bounce down here slightly and kind of unpack this saturated and unsaturated first. So I have a little cup of water, hopefully you guys can see, and I have my solute. It's going to be salt in this case. So I'm obviously going to pour or sprinkle some salt into my solvent water, and I see it's at the bottom. Now, if I take a spoon and I start to mix it up, what you're going to start to see is that salt is going to start dissolving. Okay, if I'm able to keep dissolving stuff into my water solution, I still technically have an unsaturated solution. You're like, yep, but it's looking all good to me. It's looking all good to me. Yep, let's see what happens now. Oh, still got more salt to dissolve. So I'm going to keep mixing it up. But the thing here is that at some point, all of that salt will hopefully get dissolved. And you're going to be like, great, it's at saturation. Probably not. Okay, so if I've dissolved all of the salt, that's still not saturated. Well, how do you know when it's saturated? I got to keep adding more salt until no longer, no matter how much I stir it, no more solute dissolve. So I'm not going to waste time doing this, but you get the point, okay? So when things look they're evenly mixed, it does not mean it's technically saturated. It could still have the ability to dissolve more solute. Once you get to the point to where all of the solute has been dissolved and you still add more and it keeps dropping down to the bottom, that's where you're going to get saturation or a saturated solution. Very cool. So this is all good and fun. So unsaturated is where I can continue to add more solute and it still will continue to dissolve. Saturation, when it's like, nope, I've added the maximum amount. Everything else, thank you very much, is going to keep falling down to the bottom no matter how much you stir. Now, the next type here is a super saturated solution. Now, this one I'm going to be very technical with. A super saturated solution is a solution that has more solute than the saturation amount. Well, how can I do more stirring? No, that solution needs to be heated super high, and while it's hot, you're adding more solute to it, and then it will be cooled down low. I do that process probably a few times to force that solution to be like, you can dissolve more solute than you should be able to do. Okay, so that's a very, very, very confusing situation probably for the solvent, because it's sitting there being like, wait a minute, why do I have so many solute particles? This is impossible. So a supersaturated solution is also really fragile, because if it is slightly disturbed, meaning you knock on the side of the glass, or if you add one more piece of solute particle to it once it has been cooled, it will actually crystallize in this super crazy way out of solution. Okay, now if you'll notice, I did this because I'm being super technical. A lot of people say, yes, if I'm above the curve, I'm a supersaturated solution. But because to get a supersaturated solution from this crazy way, we're going to call above the curve here something else when we talk a little bit more in depth about solubility curves. So wait with me. Let's get to the exciting stuff though. So how am I supposed to prepare this supersaturated solution? So I've got a saturated solution, which means no more solute can possibly dissolve. I heat that guy up. I add more solute, and then I cool it down, and then that sits as a supersaturated solution. And like I said, any slight disturbance or seeding will allow the solute to kind of realize what it has been doing and actually crystallize out of solution. So I thought we could look at an example of seeding of a supersaturated solution of sodium acetate.
Okay, just really quick, I'm going to add one tiny seed crystal. I'm not sure if you can see on the tip of that scoopula there. Right at the tip, we're going to add that to my supersaturated solution of sodium acetate. And we will see it go from a supersaturated state to a saturated state in just a few seconds. Isn't that cool? So we see that the sodium and acetate ions recognize the crystalline structure of that seed crystal I just added, and they add to it, and we form one big crystal. Now when I tilt this to the side, you can see it looks like a big chunk of ice, doesn't it? So now we're back. There's a little bit of water in there. You might be able to see it, but we're back to our saturated state right now. So we've gone from supersaturated to saturated in just a couple of seconds.
So as you can tell, creating a supersaturated solution is a very, very unique, not super common thing that we're going to get typically in our normal everyday lives. But it is when you have a lot more solute dissolved in a solvent than you should be able to have. So let's unpack these solubility curves a little bit more, okay? A solubility curve shows the amount of solute that's needed to be dissolved at varying temperatures to create a saturated solution. Here, usually we show a lot of different types of solutes on one solubility curve to where we can compare their relative solubilities to different substances. So we can use the solubility curve to determine the degree of saturation. Am I saturated? Am I unsaturated? What's going on here? So let's practice looking at this. It says, if your point, what do you mean by point? If the amount of solute in the temperature that I'm looking at, if that meeting point is on one of these curved lines, that is an example of the solution being saturated. So my example here, as I'm focusing on the line for KClO3, potassium chlorate, if I have 30 grams of potassium chlorate and yes, 100 grams of water, because that's what this y-axis is measuring for that solvent, at 70 degrees Celsius, so here's my temperature, where those two lines meet, if it's on the line, that represents a saturated amount, okay? Now, if the point is below the line, meaning where my X and my Y come together will fall below the curve that I'm looking at, that solution would be unsaturated. So here an example would be 10 grams at 60 degrees Celsius of that same potassium chlorate, noticing it's below the line, which is really exciting. And if the point, oh, here we go. If the point is above the line, the solution is, you're like, yeah, supersaturated. No. Y'all just watch the video on how wackadoo getting a supersaturated solution is. Here, just casually raising the temperature and adding more solute, what's going to actually end up happening is I'm going to still have a saturated solution, but I'll have just excess solute that falls down to the bottom. Okay, so my example here was 30 grams of potassium chlorate and 40 degrees Celsius. Okay, that point meets above that line. So I've got a saturated solution, but there now is excess solute at the bottom of that solution. So super saturated solutions, as cool as they are, we technically cannot identify them on a solubility curve because this is just a strict change in temperature. It's not representing at all that super high heating and cooling down process that we have to do. So I'm being technical, but I'm being correct here. Okay, so let's do some practice. You're like, this is so easy. Well, for some reason, maybe I'm a dum-dum, but my brain like has to work really hard for these. So it says how many grams of sodium chloride will dissolve in 100 grams of water at 35 degrees Celsius. You're like, what is even happening here? What I find to be helpful is to first zone in on what the solute is, what substance, which curve am I looking at? Well, it's sodium chloride. I'm like, okay, there you are right there. I know I'm going to be doing something like below, on, or above the line, all that fun stuff. It says how many grams of sodium chloride will dissolve in 100 grams of water. The first number you're seeing is like 100 grams of water. You're freaking out. Well, guys, everything's in 100 grams of water. So you can pretty much ignore that. And the temperature that I'm looking at is 35 degrees, right? So 35 degrees, perfect. How many grams at 35 degrees? What do you mean, how many grams at 35 degrees? When I say will dissolve, that is being like, well, what can I do to get to a saturated solution here, okay? So that means I will be reading 35 degrees to get to the line. That's how many grams will dissolve, and how many grams on that, if I extrapolate back to my y-axis, I get about 35 grams of sodium chloride. That is how much will dissolve at 35 degrees Celsius, okay? All right, another way I can ask a problem on solubility curves. What is the solubility of sodium nitrate at 20 degrees Celsius? Just like last time, what curve am I looking at? Sodium nitrate, he way up there, right? And my temperature they've given me is 20 degrees Celsius. Great. And what is the solubility? Well, guys, solubility is the amount that can make a what solution? A saturated solution. So I'm just saying, hey, at that temperature, how much will get you to the line? Well, that how much is about, 88 grams of sodium nitrate in obviously 100 grams of water. All right, next one, it says if 40 grams of potassium nitrate is dissolved in 100 grams of water at 55 degrees Celsius, what type of solution will form? You're like, oh my gosh. Well, we know the 100 grams of water is not relevant because that's what this graph reads. They gave me a technical amount of solute, 40 grams, and they gave me a technical amount of, or the technical temperature at 55 degrees Celsius. Well, which curve am I looking at here? Potassium nitrate, let's see, there he is. Okay, if I extrapolate out 40 grams and 55 degrees Celsius, where those 2 points come together, is that above, on, or below the line? It is below the line. So the type of solution that is indicated by below the line is an unsaturated solution. Very cool. All right, what about at 20 degrees Celsius? Meaning same amount of solute, 40 grams of potassium nitrate, but now I'm making it a little bit of a cooler temperature. Does that change what type of solution I'm going to be? Let's see what happens if we move to 20 degrees Celsius. Oh, 40 grams at 20 degrees Celsius, I'm a little bit above the line. So me being technical, that's not super saturated, that is saturated with excess solute. Cool. Last type of practice problem that we're doing today. This one's a good one. It says, how many grams of lead 2 nitrate will dissolve in 200 grams of water at 50 degrees Celsius? You're like, why did she bold and italicize 200 grams of water? Well, you guys, first of all, lead nitrate is the curve that we're looking at here. But you notice the 200 grams of water. This graph only shows in 100 grams of water. Well, that is okay. You guys, we can be so smart here, okay? I can just use my graph to figure out how much solute will dissolve in that indicated 100 grams of water. And then I can do something fun like multiplying that by 2, and that will tell me how much will dissolve in not 100, but 200 grams of water. Okay, so let's see if we can do this. I'm at 50 degrees Celsius. How many grams will dissolve? Well, will dissolve. That means get me to the line. How many grams will dissolve on that saturated point? It is about 85. So that's 85 grams can dissolve in 100 grams of water. Well, then how many can dissolve in 200 grams of water? Multiply 85 by 2, and you got 170 grams of lead to nitrate in those 200 grams of water. So that's my solubility curves. Now, this next topic is, I think, very, very, very intuitive. So I'm going to go kind of quickly through this. But these are some factors or things you can do to affect the rate of dissolving. And when I say rate, I mean the speed of dissolving something in a solvent. So there are 4 things that affect the rate of dissolving, or how quickly something dissolves. The first thing that I can do is I can increase the surface area. Like, oh my gosh, what is this with this surface area term? That just means breaking things up into smaller pieces, like crushing something up. So that means if I crush something up with a higher surface area, the molecules on the inside are more exposed, meaning the solvent can kind of come into contact and break them apart further more quickly, okay? The greater the surface area, which means the smaller the particle of the solute, the greater the particles are in contact with the solvent. So if I increase my surface area by crushing it up, then I increase my rate of dissolving. Very cool. Number 2, the next thing I can do is agitation. Agitation is a super fancy word for shaking something, disturbing it, like aggressively mixing them together. So stirring will move around the particles, causing more, oh my gosh, collisions, making the solute come into constant contact with fresh solvent every single time. So it helps break apart by making that solvent kind of, actively chew away at my solute particles. Y'all saw me stirring my salt water with a spoon. I was agitating it. So increasing the agitation will increase the rate of something dissolving. Amazing. The third thing I can do is I can mess with the temperature. And I've broken this temperature part up into 2 parts. First, I'm going to focus on how temperature affects liquid and solid solutes. You're going to want to heat them up, because heating up or increasing the temperature, we know, increases the average kinetic energy of my solvent particles, and it will increase the amount of collisions with the solute, which will allow them to kind of chew away and mix them into the solution. That's why when I put sugar in hot tea, the sugar dissolves much more easily when the tea is hot than if it was cold, right? Okay, so for liquid or solid solutes, we want to heat them up. So increasing the temperature will increase the rate or the speed at which something dissolves. But what about gases? Oh my gosh, you guys, gas solutes, exact opposite. We want to cool them down for them to stay dissolved in solution. Because heating, yes, it increases the average kinetic energy, but for gas particles, increasing the average kinetic energy will allow them to actually want to escape the confines of a watery type of a solution. This is why if you leave a soda can outside on a hot Texas day or in your car, the temperature increases, right, which causes the gas particles to escape the solution, which means the pressure in the can increases, which means your can explodes. So yeah, we do not want a hot can of soda, okay? So for gas solutes, it's the opposite. You want a cold temperature to increase that rate. It slows them down and it shoves them inside there a little bit better. Speaking of my last one, pressure. This is also split into 2 different solute categories. My liquid and solutes, how are they affected by pressure? They are not. There's no effect of pressure on the ability for liquid and solid solutes to dissolve. That's just because liquids and solids are not compressible. I cannot squeeze them together to make them take up less space. Gases, you guys, are super compressible. So they are probably affected by pressure. And let's see in what way. Pressure, your gas solutes, you want to push them in there. High pressures force my gases to stay in solution, okay? If you think about a bottle of soda or a can of soda, whenever you open that up, you hear a and you probably see some bubbles rise to the top. That is because the bubbles are actively trying to escape the solution because you have released the pressure. If I hold that soda can out just for a long time open, eventually it's going to go flat. That means all of the carbon dioxide bubbles have left the solution because of that low pressure. Okay, that's why I need a closed top on anything that's carbonated to keep those gas particles in solution. So for my gas solutes, we want high pressures to shove them in there, okay? And that will increase the rate at which they will dissolve, which is very, very exciting. Okay, now I want to focus specifically on water. We said in chemistry, when I do solution chemistry, I'm dealing with chemical reactions involved in an aqueous solution of these substances. This is water. Water is so special because water is the universal solvent. We now know that solvent is the thing that does the dissolving, or the environment at which the solute is able to kind of move around in. Okay, so water is the universal solvent. And I thought we would learn a little bit more. Why? First of all, here's a cute cartoon. It's two little water droplets. And it says, oh no, it's humaning again. There's little humans falling from the sky. It's not raining, it's humaning. It's not funny, but I enjoy it. Okay, we've learned this before. Water is polar. Within a water molecule, the oxygen atom, okay, has a greater electronegativity than the hydrogen atoms. So we know if one atom in a chemical bond has more electronegativity, which means it wants electrons more, it's going to pull more unevenly on that shared pair, and there will be a slight partial negative dipole on that atom, okay? So as a result, the oxygen will be slightly negative and the hydrogen will be slightly positive. So this polarity will allow for very strong hydrogen bonding IMFs between the molecules, right? So hydrogen bonding is the strongest type of intermolecular force, and it occurs when you have hydrogen that is bonded to either a nitrogen, oxygen, or fluorine. We've totally got an oxygen in there in that water molecule, and it allows for a lot of cool stuff because of this polar hydrogen bonding nature. As a bonus to this polarity, you guys, because water is kind of like a magnet with a positive end and a negative end, water can be attracted to many different types of solutes because it actually gets in there and by electrostatic attraction can help break apart stuff and help surround my solute particles. Okay, and as a review, when water is the solvent, those types of solutions are called aqueous solutions. So I thought I would kind of help visualize this maybe a little bit more down here. Let's say this is my, oh, look at this, look at this transition. I'm sliding this guy in here. I love this so much. So this is a crystal structure of maybe some sodium chloride, where the silver ones are going to be my sodiums and the green ones are going to be my chlorines. If I were to put this guy into water, what would end up happening is, here's my cute little Mickey Mouse water molecule. We said this part of the water molecule is negative, and this part down here where the hydrogens are is going to be positive. Well, my sodium ion, when he gets close to water, he's going to make a positive ion charge, right? Well, the part of the water molecule that's going to be attracted to a positive sodium ion is going to be the negative oxygen end. So in this picture here, if I have a sodium ion right here, you'll notice that all of the oxygens are oriented around the positive sodium, because we know that opposite charges attract. Now, similarly, if I have a negative chloride ion that the water molecule pulls off of this crystal lattice structure, well, negatives are going to be attracted to positives. Well, the positive part of the water molecule is the hydrogen end of the water molecule. So on my diagram right here, I totally see each chloride ion is going to be surrounded completely by the positive end of the water molecule, the hydrogen end. So that's really cool, because y'all, a lot of things in this world have some sort of a charge, and water molecules can be like, yeah, I can totally handle no matter what you throw at me, which is really fun. Okay, now we've used the terms polar and nonpolar, blah, 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 blah. So there's this kind of technical, no, this is not technical at all. There's this just kind of loose understanding of like dissolves like in science. Now, like dissolves like means polar solvents, like water, for example, will dissolve other polar things. A polar thing dissolves a polar thing. Like dissolves like. Two things that are the same will dissolve well in each other. Okay, so polar solvents like water will dissolve other polar molecules. Let's just pause there and not read the rest. Well, we know a polar molecule has a positive end and a negative end, and a polar molecule has a positive net end and a negative end. Those are like two little magnets. Of course they're going to want to stick together. So that's where the like dissolve like comes into play. Not only do polar solvents dissolve polar molecules, but they dissolve ionic compounds, meaning things that break apart into positive and negative, completely positive and completely negative ions. Well, it's just, we got charges here, you guys. Charged particles will want to interact with other charged particles. This also means not only polar dissolves in polar, but nonpolar solvents dissolve in other nonpolar molecules. So these are two like terms. Down here, I've got a cute little chart right here, okay? I have my polar solvents, right? It's showing me here my polar solvents like a water. Ionics, yep, they'll be soluble in a polar solvent. Polar solutes, yep, they'll be soluble. Non-polar stuff in polar, does not work well. Now here for my non-polar solvents, will a non-polar solvent dissolve in ionic? No. Will it dissolve a polar molecule? No. Will it dissolve a non-polar molecule? Yes. So this is the like dissolves like, and as you can tell, if I have somebody who is not like the other, a polar and a non-polar trying to mix together, they do not dissolve. This is why oil and water do not mix. Water is super duper polar and oil is non-polar. They are not at all the same. They do not play nice together. They do not hang out together with each other, okay? So the oil layer will physically separate away from my water layer no matter how much I try to encourage it to mix, okay? So they are not alike. They will not dissolve. And here's a cute little cartoon. It says, help, help, I'm dissolving. But bears are insoluble. That's easy for you to say, you are not polar. The polar bear is dissolving in the polar water. Oh, it's funny. Okay, last topic that we're going to talk about, and we've kind of mentioned this before, is conductivity of aqueous solutions here. Some compounds in aqueous solutions conduct electricity, and some don't. It all depends on what is the type of solute that is in that water. An electrolyte is a compound that conducts an electric current in an aqueous solution or in a molten state. An electrolyte solution contains charged particles, ions, which can move and therefore transfer the electrical charge, okay? So far, I think we've seen this term electrolyte before, but now we're going to kind of review it a little bit more. Ionic compounds, we said it, well, first of all, being able to conduct electricity is all about what type of a compound you are. Let's zone in on ionic, and then we'll focus on covalent. Ionic compounds are made up of a metal cation and a non-metal anion. These compounds will dissociate into ions. This is a super important term for us to get today. Dissociate. Dissociate means to break apart into ions, okay? And I'm actually kind of maybe visualize this down here. What we have down here is, well, here's my crystal lattice structure, okay? If I dropped a whole bunch of sodium chloride particles into water, all of them would spread out, okay? If I focused on just one individual formula unit of a sodium chloride particle, I put him in water and he dissociates. And that's important because I've separated them apart to where I have a positive sodium ion and a negative chloride ion, okay? So when you think ionic compound, think dissociate. Dissociate. The ions break apart to where they are dissolved positive and negative charges in solution. As a result, these ionic compounds, when they're in water, they can conduct electricity, so they are electrolytes, okay? That's ionic compounds. Dissociate, conduct electricity. But what about my covalent compounds? Well, the covalent compounds, you guys, the molecules stay intact. They spread apart from each other, but they do not dissociate. So if I were to say, I'm making a soda, let's say this, okay, and I have carbon dioxide molecules dissolved in water, right? So I go put them in water and they're going to spread apart, but I'm not going to be breaking any of these atoms off of each other and removing them from the molecule to create charged ions. They're just going to spread apart, okay? So the molecule itself actually stays intact, and this is super different than what would happen if I had a sodium chloride. They will break apart. This just stays intact and separates. So looking here, I just said, okay, if I take solid sugar and I put it in water, I still, that same formula, right, you guys? It's just now, I just indicated, oh, he's dissolved in water, by the way, okay? But on the previous slide, I had my solid sodium chloride. I'm showing in an aqueous solution, and it actually physically separates into ions, okay? So they do not dissociate. Dissociation, meaning breaking apart in ions, is not the same thing as dissolving, okay? Sugar dissolves quite well with water. Dissolving means to mix evenly in the water solution, right? Okay, both covalent and ionic compounds can dissolve, but dissociation is a further piece tagged onto that, and that's involved in actually splitting apart, making ions. Sorry, that was a big tangent. But covalent do not dissociate, which means I'm not getting any charged particles in solution with this poor guy. I am not. Oh no, no positive, no negatives. Well, I need ions to conduct electricity, so covalent compounds, even when they're dissolved in solution, are going to be non-electrolytes. They cannot conduct electricity. So review, ionic, they dissociate into ions, and my covalent, they do not, they stay intact. So my ionics are electrolytes and my covalents are non-electrolytes. Let's watch a video to see, I don't know, how this would affect a light bulb lighting up.
So what I have here is an apparatus. It has a light bulb with a positive and negative end, and what you can't see is that I have it plugged into the wall. The thing is that the light bulb isn't lighting up yet, okay? But there is electricity going through it, but nothing's completed the circuit for the light bulb to light up. So what I'm going to do is this. I'm going to place this light bulb inside the sugar water to start. If the sugar water conducts electricity, this light bulb will go on. So let's see if that happens. No, nothing happens. All right, so an explanation for that is sugar, which are covalent compounds, right? It's a molecule. When they dissolve in water, they really don't break apart into positive and negative ions, so therefore, they're not electrolytes. They don't conduct electricity. Again, think of the word electrolytes and electricity. There's a similarity there and a relationship. All right, now I've got my salt water. Let's see if we put this into the salt water, if it'll conduct electricity. And lo and behold, it does. Can you see that? When I put the light bulb electrodes in the salt water, it conducts electricity. So what's happening here? Well, when we dissolve the salt into the water, it started breaking up into its positive and negative ions, positive sodium ions and negative chlorine ions, technically called chloride. By doing so, there are positive and negatives in this water, and when we put the electricity through it, the electricity can pass from one electrode to the other to complete the circuit so the light bulb can light up. So when we think about properties of ionic compounds, we say that they tend to be electrolytes, meaning they often can dissolve in water, and when they do, they conduct electricity. Unlike molecular compounds, which have covalent bonds. These guys don't break down enough, and they can't create that positive and negative end that can conduct electricity.
So yes, ions are needed to conduct electricity, okay? If I have ions in solution, it's an electrolyte. If no, it's a non-electrolyte. There is kind of an in-between gray area here to where if we have a few amount of atoms or particles dissociate into ion, but not all of them completely, you can be somewhat in the middle as a weak electrolyte. But today's lesson is strictly just focusing on how to identify the difference between strong and non in terms of the electrolytes. So that was it. That was our first lesson, was on just general solutions, some terminology, talking about how things dissolve, right? And then we're going to take this information moving forward into how this relates into what chemical reactions I can do in these environments of an aqueous solution.